So this is the problem from the pre-class quiz. Air has a density of 1.2922 grams per liter at standard temperature and pressure, which for gases is 0 degrees Celsius and 1 atmosphere of pressure. Assuming air is composed of only nitrogen, N2, and oxygen, O2 gas, what must the percentage of moles of nitrogen in air be? All right, so we know the molecular weight of N2 is 28.02. We know the molecular weight of O2 is 32.0. We are solving for the percentage of moles or the mole fraction of N2 in air. Okay, so how can we get there? So we know we have this mixture, and we know that we can work between the partial pressure or the total pressure of the system and the amount of moles. So we know we have a certain density of air. Why don't we solve for the number of moles? Now, in this problem, we aren't given a value for the volume of air. However, to ease the calculations for this problem, we can assume a volume of 1 liter to make our lives easier mathematically. So let's start by solving for the total number of moles, and then we can use this, or the total number of moles, which in this case would be the average moles of air, moles of N2 and O2 in the air, so that average will be reflective of the mole ratio. But let's start by solving for that N. So if we have PV equals nRT, we're going to rearrange our favorite ideal gas equation to solve for N. So N is equal to P times V over RT. All right, so we know we have a pressure of 1 atmosphere. We are assuming 1 liter of volume. And so we're going to use our gas constant that has the units of liters ATM, so 0.08206 liters ATM over mole K. And then our temperature is 0 degrees Celsius, or 273 Kelvin. All right, so pause, go through, crunch the numbers, and then start back again. All right, so if we do this calculation, we know that we have, and then in 1 liter of gas, our average number of moles is 0.0446 moles. And this average number of moles is coming from some combination of N2 and O2. So what we can do is we can use our algebra to solve for the relative amounts. So we know that our average number of moles, which in the average molecular weight of these moles, the molar mass or the molecular weight average, is equal to the mole fraction of N2 times the molecular weight of O2 in grams per mole, plus 1 minus the mole fraction of N2 times the moles of the other compound, the molecular weight of the other compound, which would be oxygen, so 32.0 grams per mole. So if we multiply our x's by our values, we get that our average molar mass is equal to 28.02x plus 32 minus 32x. So now what we can do is we can rearrange to solve for our mole fraction of x because we know our average molar mass here. All right, and the reason why we know our molar mass is because we know that in 1 liter of gas, our molar mass average here is equal to the number of moles. Our molar mass average is equal to the number of grams that occur in a mole. So we know we have a density of 1.2922 grams per liter. And if we have 1 liter of gas, it contains 0.0446 moles. So what we can do is if we multiply this value by 1 liter, we get 1.2922 grams. And in that same liter, we also have 0.0446 moles. If we do the math and divide this out, we get an average molecular weight of 28.97 grams per mole. So now we can plug that average molecular weight back into our equation. So we have 28.97 grams per mole is our average molecular weight, and that's equal to 28.02x plus 32 minus 32 times x. Now we can add our x's together, do some rearranging, and this is what we get. We divide both sides by negative 3.98x. We get x is equal to 1.31. Or excuse me, let's erase that right quick. 3.03 divided by 3.98x gives us 3.98 gives us 0.76. So that means the mole fraction of N2 would be 0.76, or approximately 76%. So it means 76% of our atmosphere is oxygen, or is nitrogen. So to find the percentage of oxygen, we would do 100 minus 76, and that would give us 24% oxygen. All right, well, I hope this video has been helpful to you. Enjoy working with gases.